Swayam Prabha. Digital India. Educated India.
So, in the last lecture we derived the final element formulation for the beam that has externally applied load, which is dampened out by shape memory alloy wires. Now, today we will see how the forces F h bar, F v bar and M can be calculated based on the displacement that are experienced at node number 2 n plus 1, node number n plus 1. So, to do that, let us look into the diagram. So, here this portion shows only the part of the beam which is from x equal to 0 to L A. Now, due to the bending of the beam, this point moves here. Now, we have to find out the final length, which is small l plus delta l. So, small l is the initial length of the shape memory alloy wire and L plus delta L is the final length after the deformation. So, we have to find out this final length L small l plus delta L. So, the slope here is, this slope is del w by del x, because if we consider the Euler-Bernoulli assumption, then the plane section remains plane before and after bending. So, this slope is also del w by del x. Now, if this slope is del w by del x, then this offset is del w by del x, which is w prime multiplied by T b by 2. So, in this diagram w prime is equal to w comma x equal to del w by del x. Then if we know this quantity, then finally after applying trigonometry, it can be shown that our L plus delta L whole square is equal to H minus d 2 n plus 1 whole square plus L A minus T b by 2 d 2 n plus 2 whole square. Here h is this vertical dimension, and as we know that d 2 n plus 1 as per our degree of freedom nomenclature is equal to w at x equal to L A, and d 2 n plus 2 is equal to del w by del x at x equal to L A. And also we know that small l square, the undeformed length, is h square plus l square. Then subtracting we can get 2 l, 2 small l del l equal to minus 2 h d 2 n plus 1 minus L A T b d 2 n plus 2, and then it becomes del L equal to minus sin theta d 2 n plus 1 minus cosine theta into T b by 2 d 2 n plus 2. So, strain in wire 1 increases by an amount epsilon 1 c, which is equal to del L by L, and that is equal to minus sin theta d to n plus 1 divided by small l minus cosine theta T b by 2 L multiplied by d to n plus 2. Now, we have wire 2 below it. So, the upper wire we denote it as wire 1, and then below also we have a wire, and the wire below is wire 2. So, the wire that is positioned here we call it wire 2. The upper one is wire 1 and the wire below is wire 2. So, because they are symmetrically placed, the amount of strain would be same here, but opposite, because this would, if this is experiencing a negative quantity as a strain, this would experience a positive quantity as a strain, it will try to increase in length. So, strain in wire 2 increases by epsilon 2 c, which is equal to minus of epsilon 1 c. Now, let us define a quantity epsilon 1 c is equal to epsilon 2 c is equal to epsilon c. Now, we can say that strain in wire 1 is epsilon 1 equal to epsilon p plus epsilon 1 c, where epsilon p is the amount of pre-strain in the wire. So, when the beam is undeformed, the amount of pre-strain in the wire is epsilon p. So, epsilon p is pre-strain in the wires, and they should be same because they are symmetrically placed when the beam is undeformed. And strain in wire 2 is epsilon 2 equal to epsilon p minus epsilon c. We have already defined a quantity epsilon c. So, let us not use the suffix 1 or 2. So, epsilon p plus c and epsilon p minus epsilon c. Now, if I know these strengths, we can find out the stress by using the constitutive relation of the piezoelectric materials that we discussed. So, stress in wire 1 can be found from the equation sigma 1 minus sigma 1 0 is equal to E xi 1 multiplied by epsilon 1 minus epsilon 1 0 plus omega xi 1 multiplied by xi 1 minus xi 1 0, and there could also be a term capital theta multiplied by the temperature difference. However, in this entire process the temperature is remaining fixed. So, that quantity does not have any contribution, and anyway even if there is some temperature difference, we have seen that the contribution due to that capital theta term is generally negligible. So, we do not have that term. So, here xi 1 is the Martensite volume fraction in wire 1, and epsilon 1 0 is the initial. So, it is not epsilon 10, it is epsilon 1 0, maybe we can put a comma here. 0 means the initial configuration, epsilon 1 means the stress in wire 1, 0 means initially how much it was. So, there is a change in the stress in wire 1. Similarly, here also it is it is sigma 1 minus sigma 1 sigma 1 0, that is a change in the stress in. So, here we have this term sigma 1 minus sigma 1 comma 0. So, it is not sigma 10, it is sigma 1 comma 0, and that signifies the change in the stress in wire 1. Similarly, I have epsilon 1 minus epsilon 1 comma 0, and that signifies change in the strain in wire 1. So, it is change in the stress in wire 1, this is the change in the strain in wire 1, and similarly, this is the change in the Martensite volume fraction in wire 1, and they are related through this constitutive relation. Again, we know that this equation is a highly nonlinear equation, because this xi 1 is a function, is a nonlinear function of sigma. So, xi 1 is nonlinear function of sigma 1, and we can use it Tanaka model or Liang and Rogers model or Brinson model, whatever model we use. This is a nonlinear function of sigma 1, and we have seen how to solve this equation using a technique, iterative techniques like Newton-Raphson technique that we discussed in the last lecture of the previous week. So, accordingly we have to find this out based on some initial and final strain. So, if I know the initial strain, if I know the final strain, we can find this quantity, find the stress out by solving the nonlinear equation. So, that makes the entire solution of the finite element equation highly iterative. So, now let us discuss how we can solve it. So, here is the flow chart of the iteration procedure. So, at first we guess epsilon c, because let us suppose that we are solving a static problem, right. So, for a given load, for a given static load, we first find out what is the amount of displacement, what is the deformation in the beam. So, for that condition we do not know the epsilon c. So, we guess, that is what we have to find out. So, let us guess epsilon c, guess some value, and based on the guess we find out sigma 1, find out sigma 1, sigma 2. So, in this case our epsilon p becomes the initial strain sigma 1 0, and the final strain is epsilon 1, which is equal to epsilon p minus epsilon p plus epsilon c for the wire 1, and for the wire 2 it is epsilon 2 equal to epsilon p minus epsilon c, and for both the wires our initial strain is epsilon p. So, based on that we find out our stresses, and again this itself is a iterative procedure. So, to evaluate this block itself we need to do the Newton-Raphson based iteration and find out sigma 1 and sigma 2. Once we get our sigma 1 and sigma 2, we can find out the amount of forces in the wire, we can find out the amount of tensions in the wire. So, sigma 1 is a stress in wire 1 and sigma 2 is the stress in wire 2. If I multiply those by the area of cross section of the wire, we get our tension T 1 and T 2. So, find T 1 equal to sigma 1 A and T 2 equal to sigma 2 A, where A is the cross sectional area of SMA wires. If I get my T1 T2, I can find out the quantities F h bar, F v bar and m bar. Once I know those quantities, now my force matrix, force vector in the finite element formulation is defined. Now, for that known force vector, I can find out d. So, now please understand, here we are solving a static problem, we are assuming that the applied force is time independent. So, in this case we would just solve this equation k d equal to f. Then once we have found out d, we know what our d 2 n plus 1 and what our d 2 n plus 2 and what is our d 2 m plus 1, and then based on that we find out again epsilon c. Now, the question is whether this epsilon c or the previously got epsilon c is agreeing or not. If they are not converged, we have to repeat the procedure. If they have converged, we can stop the procedure. So, now epsilon c converged. If the answer is yes, then we can exit, and if the answer is no, again we go back and feed that newly obtained value of epsilon c and repeat the procedure until and unless the improvement of epsilon c stops. So, until and unless the convergence of epsilon c is obtained. Once the convergence of epsilon c is obtained, the corresponding d is our obtained value of the nodal degrees of freedom at different node points, and that gives us the solution. So, it is a solution of the static problem. So, static solution. So, applied load P does not change with time. Now, what if we want to do the dynamic solution? That is the goal of this work, because we have added a damping and our force P is a time dependent force and the vibration caused due to that has to be dampened out. So, here let us go to the dynamic solution. P is time dependent. Now, for dynamic solution we already discussed the various algorithms to do the time marching. One of them was the Beta-Newmark method. We did this discussion in week 5. So, here in the Beta-Newmark scheme it goes like this: at every time step n plus 1 we know the quantities at the previous time step. So, at the n plus 1th time step we know d double dot at the time step n, we know d dot at time step n, and we know d at time step n. So, based on those known quantities we find out our d double dot at n plus 1, because in this expression all the quantities like d double dot and d are from the previous time step. So, we can find this out. After we find out d double dot at n plus 1, we can find out our dn plus 1. After we find out dn plus 1 and d double dot at n plus 1, we can find out d dot at n plus 1, and the time marching proceeds. Then we go to the n plus 2th time step, and at that time step n plus 1 quantities at n plus 1 are known to me. So, I can do the same thing. However, here because this problem is highly nonlinear, evaluation of this d double dot at n plus 1 involves the iteration, because here I have the force matrix here. Now, to do this again we do the same procedure. So, whatever iteration we defined here, that entire iteration has to be done to solve this equation. So, for solution of this equation, this iteration has to be repeated. So, within each time step we have to find out d double dot at n plus 1 by this kind of iteration, and after that we can find out d dot at d and d n plus 1. So, here if I want to find out this by iteration, again I make a guess of epsilon, and based on the guess of epsilon that we make, we can find out d dot at n plus 1, and that will give us d at n plus 1, and once we get that and we can find out d dot also, and then once we get that d at n plus 1, we can find out the new epsilon, and again the procedure is repeated till my epsilon converges. So, within each time step the evaluation of these quantities, they involved the iteration that was discussed in the previous slide, and it continues. So, that is what about the iterative solution of the finite element equations that we get. Now, if we want to solve the same problem, using the Reed's method, we can do it in this way. Again we can write the variational form. And we have the last quantity here. The virtual work is at the point L B, because that is where we are applying the externally applied load. Now, here instead of having a localized basis functions, what we assume is W as a function of x and t is phi x multiplied by phi j x multiplied by q j t, where phi j is a function of x, known function of x, and q j is unknown function of time. So, again we follow the same procedure that we discussed for Reed's method. We put everything in the virtual work equation, and then finally we get the quantities as a set of ordinary coupled differential equations which looks like this, and then we have m I j is equal to 0 to L phi, I should have the rho a also, rho a phi I phi j dx, and then we have k j is equal to E I phi I comma x x phi j comma x x dx, minus we have f h bar 0 to L a. Okay, so, this quantity is 0 to L a, not L, phi I comma x phi j comma x dx, and then we have the force as f v bar multiplied by phi I evaluated at x equal to L plus m bar multiplied by phi I comma x evaluated at x equal to L L a plus p multiplied by phi I evaluated at x equal to L a. So, this is the set of ordinary differential equations that we get when we use the Reed's method. In the finite element problem, our force matrix was mostly 0 except for few places. Here the force matrix is populated fully, and then the solution remains same. We have to iteratively find out Q. So, there we are finding out D, here we will be finding out Q, and the iteration has to be in such a way that epsilon c converges. Now, if we want to simplify it, let us assume that we have a one term approximation for W, and the approximation is W by L x by L cube multiplied by Q1. So, that gives the equation as L by 7 Q1 double dot plus 12 multiplied by EI 12 EI by L cube minus 9 FH bar 5 L multiplied by Q1 minus F V bar L A by L. So, it is L suffix A minus 3 m bar L A square by L cube plus P into L B equal to 0. So, here I have the force terms directly written in terms of F B bar and m bar. So, here I have just one equation, and this equation now has to be solved again iteratively. So, we have to, like we discussed, we have to do the time marching, and within each time step we have to iteratively find out these Q's, so that epsilon c converges. So, that is what. So, that is how this problem can be solved. Now, shape memory alloys are used as actuators also. In that case, we have to give thermal actuation. So, for the same configuration, if it has to be used in actuation mode, so application as actuator. For the same problem, if we want to use the same configuration, I mean the shape memory alloys put in the same configuration as actuators, in that case let us assume that both the wires is in the Martensite phase. So, Martensite phase with some permanent deformation. Now, when due to the application of this force P, this beam wants to go up, in that case what we can do is, because the upward movement of P, upward movement of the beam would try to extend this wire. Now, if I give a heat actuation here, then the heat actuation would try to take the wire to its previous shape, which has a length less than the length that is here. So, that would generate an actuation force to the beam in the bottom direction and would try to prevent the upward movement. Similarly, when the beam tries to go downward, we can excite this actuator thermally, and that would try to bring this shape memory alloy wire to the austenite phase. So, it would try to reduce the length of it, and then the beam would experience an upward force. So, that is how it can be controlled by thermal actuation. Now, here apart from the temperature, the stress also comes into picture, because when the beam is going up or down, the stress in the wires also changes. So, the same the non-linearity still remains, which needs to be solved, but temperature also comes into picture because of the actuation, and the entire system can be designed in such a way that it has to sense, by a sensor it has to sense whether the displacement is up, how the displacement is, how the velocity is, and accordingly one of the actuators have to be excited to control the displacement. So, for this this paper can be referred to see an application like this. There are various papers which talks about applications of shape memory materials for vibration control or shape control. However, in this paper it is one of the earliest papers in this area. Here the actuation equation is much more simplified. So, this can be a good paper to start with to read those things. In this paper the system is little different from the paper that we saw before. Here we have a beam in this paper and there are two parallel shape memory alloy rods and they are connected to the beam, and this entire beam is vibrating under the action of some load, and there are some sensors which sense the displacement and velocity of the beam. Now, the formulation given in this paper includes the bending stiffness of the shape memory alloy rods at the top and bottom also, and by giving thermal excitation to one of the shape memory alloy rods based on what the sensors senses, the vibration is controlled. The formulation can be seen in the paper. So, with that I would like to conclude this lecture here. Thank you.